how the same set can be an R module for different rings R. But it's just not true that a set is an R module for every ring R. So a common kind of exam question that you might see is, here is some set that's an R module for some ring R. Is it also an S module for some other ring S? And in this video, what I want to do is show you two examples of questions like that where the answer is no. So the first one is exercise 15 in section 10.1 of Dummett and Foote. Let's say M is a finite abelian group. We know that M is naturally a Z module. So we've seen that there is a unique action of Z on M that turns it into a Z module. And the question is, can this action be extended to make M into a Q module? So what does that mean, can be extended? Well, what would we need for M to be a Q module? We would need an action of Q on elements of M. And Z sits inside of Q, like all of the integers are also rational numbers. So we would want the action of elements of Z to be the same as when we think of M as a Z module. Okay, the answer is no. And one way to say this is going to use something that we haven't actually talked about yet, but will come up soon. So we know that if F is a field and you have M being an F module, then that means that M has to be a vector space over F. So a Q module is a vector space over Q. So if M were a Q module, it would be a vector space over Q. But a non-trivial vector space over Q is infinite. Right? If you have more than just the trivial elements, then a vector space over a field has a dimension, especially, and if this group is finite, I mean, this is just not possible. So if your dimension is at least 1 and you're a vector space over Q, then you have to be infinite. But that's not really in the spirit of what we're doing here. So I want to give you a different argument that doesn't involve anything about like the dimension of a vector space. Okay, let's suppose that, so M is a finite abelian group, so its size is some positive integer n. So what do we know? We have Z is a ring with an identity, Q is a ring with an identity. So our module should be a unital module where 1.x equals x for all x in M. Let's pick a non-zero element of M. So, okay, so I guess that what I really should say is here we want M to be a non-trivial finite abelian group. If it's the trivial group with one element, you can think about what happens. So the key idea here is that we know how integers act on elements of M, but what about rational numbers? And we're going to pick the particular rational number 1 over n and ask, what is 1 over n dot x? And this is where the problem is going to come from. So we're going to suppose that we can define an action of Q on M that turns it into a Q module. And we're going to see a contradiction by saying there's no good choice for what 1 over n dot x could be. Okay, so what is 1 over n dot x? Well, it has to be some elements of our finite abelian group M. So let's call it y. So then x is equal to 1 dot x. But 1 is 1 over n plus 1 over n plus 1 over n times. So 1 over n plus 1 over n plus dot x has to be the same as 1 dot x. And if this is going to be a Q module, then it's going to have to satisfy this distributive axiom where 1 over n plus 1 over n plus 1 over n dot x has to be 1 over n dot x plus 1 over n dot x plus n times. But we know what 1 over n dot x is. It's y. So this has to be y plus y plus y plus y n times. So if M is a Q module, this has to be true, that x has to be equal to y plus y n times. But if y is an element of a finite abelian group of order n, then when you take y plus y n times, you get 0. N times y is 0 for all elements y in a finite abelian group of order n. Why is that? Well, the order of an element divides the order of the group. So you take any element and add it to itself n times, and you get 0. But now we have x equals 0. And this is a contradiction to the assumption that x was not equal to 0. So what are we seeing? We're seeing that we have this z module M, and there's no good way to turn it into a Q module because there's no reasonable choice for what the rational number, how the rational number 1 over n could act on elements of this finite abelian group. So I'll pause and erase, and I'll give you another example of a problem that's in a similar spirit. Our next example comes from the fall 2020 Algebra Comprehensive Exam. This is problem number 8. And it asks, is there a scalar multiplication from z adjoined square root of 2 cross z mod 5z to z mod 5z? So our scalar multiplication is a function from this ring cross z mod 5z to z mod 5z. It's an action of z adjoined square root of 2 on z mod 5z that makes z mod 5z into a z adjoined square root of 2 module. And the answer is no. The idea is to say, okay, we know how integer elements of z adjoined square root of 2 will have to act on elements of z mod 5z. For one thing, this is a ring with an identity, so it has to be that 1 dot x equals x for all elements of z mod 5z. And then if you know what 1 dot x is, you know what 2 dot x is, because 2 is 1 plus 1, and you can use the module axioms. But what about square root of 2? What about elements in z adjoined square root of 2 that really are not integers? So the question we're going to have to answer, one question, is what is square root of 2 dot g going to be for g in z mod 5z? And okay, this is where the problem is going to come from, but we can go even a little bit narrower and ask, what is square root of 2 dot 1 going to have to be? So that's just one element of z mod 5z, and we're going to find a problem right here. So let's suppose that, okay, I mean, what does it have to be? If this scalar multiplication turns z mod 5z into a z adjoined square root of 2 module, it's got to be some element of z mod 5z. So let's call that element A. And now, by the module axioms, if there is a scalar multiplication that turns z mod 5z into a z adjoined square root of 2 module, what has to be true? So we know what square root of 2 dot 1 is. So let's act by square root of 2 again. So square root of 2 dot square root of 2 dot 1, this is square root of 2 dot A. And in z mod 5z, you can think of each element as being like 0, 1, 2, 3, 4. So just take whatever that class is. A is represented by one of those 4 integers. So you can think of it as square root of 2 dot 1 plus 1 plus 1 A times. This could be 0 times, 1 times, 2 times, 3 times, 4 times. But every A is equal to 1 plus 1 plus 1 plus 1 some number of times. Okay, so now if z mod 5z were a z adjoined square root of 2 module with this axiom, it would have to satisfy this distributive relation. It would have to be that whatever this element is square root of 2 dot 1 plus square root of 2 dot 1 A times. But we know square root of 2 dot 1 is A. So that's A plus A plus A times. And what is that in z mod 5z? A plus A plus A, that's A times A, that's A squared in this ring z mod 5z. Okay, so, or it's A times A. It's, if you think of A as being represented by some integer, pick some integer in that equivalence class in z mod 5z, it's whatever the class is of the integer A squared. Okay, but we can think about this a different way. Right, so we have square root of 2 dot square root of 2 dot 1. And if z mod 5z is a z adjoined square root of 2 module, this element of z mod 5z has to be the same as square root of 2 times square root of 2 in the ring z adjoined square root of 2 dot 1, which is 2 dot 1, which is 1 plus 1 dot 1. And if this really is a z adjoined square root of 2 module, this has to be 1 dot 1 plus 1 dot 1, which is 2. So the element 2 in z mod 5z has to be the same as the element a squared in Z mod 5Z. The class of a squared in Z mod 5Z is 2. So, okay, so what are we getting? We're seeing the 2 equals a squared in Z mod 5Z. But a squared equals 2 just has no solutions in Z mod 5Z. If you square each of the elements of this quotient group, there just are no solutions to a squared is congruent to 2 modulo 5. So what are we seeing? There's no good choice of square root of 2.1, because any choice we make, the square of this element in Z mod 5Z has to be equal to 2. But there just are no elements that square to 2. So there is no scalar multiplication that makes Z mod 5Z into a Z adjoined square root of 2 module.